Hello and welcome to a walkthrough the exam number 2 key. I know that some people have appreciated kind of walking through the exam number 1 key, so I thought I would walk through exam number 2 key. This is not a good way to do it. And we'll just take a look and see if there's anything that I can clarify about how to answer any of these questions. So, question number 1 is, how long does it take a plane traveling at some velocity to fly around a circle with a certain radius? So, the deal is that we know the distance that it travels, 2 pi times the radius, and we know the velocity it travels. So all we have to do, if we know that velocity equals distance over time, we can figure out that the time it takes equals distance divided by the velocity. So in terms of our normal look at rotational motion, we'd say v equals 2 pi r over t, and then we would solve for t. T equals 2 pi r over v. 2 pi times the radius divided by the velocity of 100 meters per second, and we get 368 seconds. This was a question that appeared on Chapter 6 quiz, and most people got it. So I think you guys are in pretty good shape on that one. All right. Microwave ovens rotate at a rate of about 7 revolutions per minute. What is this in revolutions per second? What is the angular velocity in radians per second? So just more conversions. If you have revolutions per minute, there's 60 seconds in a minute. So we wind up with 0.12 revolutions per second. So this is kind of hard to show when I type out the answers like this, but 7 revolutions per minute, and then you put in parentheses next to that to convert minutes to seconds. There's 60 seconds in a minute. So that's how you do that. And then, if we want to get omega in radians per second, we have to know how many radians per revolution. So there's 2 pi radians in each revolution. There's 0.12 revolutions per second. Revolutions cancel, and you wind up with 0.73 radians per second. All right, another question that we've seen before on a quiz. We have a truck with a certain radius tire traveling at 25 meters per second. There's multiple ways to solve this one. I've done the V tan equals R omega solution before. In this case, I'm doing the case where we're saying the circumference of a tire is going to be 2.51 meters. So the car is going to travel 2.51 meters for every revolution. At 25 meters per second, times 1 revolution is 2.51 meters, we wind up with 9.96 revolutions per second, therefore 62.6 radians per second. Probably a lot easier to do V tan equals R omega, and then omega equals V tan 25 divided by R 0.4. And that would be radians per second. Why is that a different answer? It's not. 25 divided by 0.4 is 62.6. So you get the same answer. All right. Person is mowing the lawn. But wait a second, they're not asking us something normal with FD cosine theta. It's a conceptual question. So under what conditions would the lawnmower gain energy? Well, it would gain energy if we were to drop it off the roof of a building and potential energy turned into kinetic energy. But maybe we shouldn't do that with our lawnmowers. If we speed it up, it gains kinetic energy. If it goes up a hill, it gains gravitational potential energy. If we slow it down or go down an incline, then it would lose energy. Hey, this is kind of like lab. If you have a 75 kilogram person climbing the stairs, gaining 2.5 meters in height, find the work done. So the work that they do is going to equal their change in gravitational potential energy. The force is the force that they do against gravity, mg, and then h is the height that they climbed. So 1.84 times 10 to the third joules of work was done in order to increase their gravitational potential energy by that amount. Similarly, but a little bit different, in order to do work on this crate, shoving it up an incline, it's going to be fairly straightforward. If the height here is 4 meters, that it goes up, then we could say work equals force times distance, 500 newtons times the 4 meters along the incline. So 2,000 joules. The man also does work increasing his own gravitational potential energy. So the incline is 4 meters long. We have an angle of 20 degrees, so I can figure out the height based on that. And the height is going to be 1.37 meters. Too many emails coming in, go away. 1.37 meters. So work on the person is going to be just like climbing the stairs, mass times acceleration due to gravity times the height difference. There it's 1.14 times 10 to the third joules plus the 2 times 10 to the third joules that we did on the crate. So a total 3.14 times 10 to the third joules, the work that he does to get the crate and his body up the ramp. I guess up to the top of the ramp where it's level. I don't know. Hey, there's an auto race held on a circular track. A car completes 1 lap in a time of 45 seconds. So we know T, the period, the time it takes for 1 revolution. And we know the speed. So we want to find the average angular speed. So the average angular speed, we don't even need to know the radius yet, right? We'll figure that out later. The average angular speed is radians per second. To go around a circular track, it's 2 pi radians. We have the time, 45 seconds. So the angular speed is 0.140 radians per second. Since V tan equals R omega, now we want to solve for R. R equals V tan divided by omega. The tangential linear velocity we were given, 30.6 meters per second, divided by omega, 0.140 radians per second. Believe it or not, all of that cancels out such that we get an answer in meters. All right, if we're going to tighten our spark plug, the simplest equation that we have for torque is torque equals force times lever arm. We're given the torque, we're given the lever arm, so we want to solve for the force. Force equals torque divided by lever arm. 30 newton meters of torque divided by 0.2 meter lever arm gives us 150 newtons of force required. 2 people start in the same place and walk around a track, walk around a circle of a, I don't know what this is, a lake, a round man-made lake or something. Here's the deal. Between the 2 of them, they want to encompass the whole thing. So they're going to head off in opposite directions, and together they need to cover a distance of 2 pi radians. So the total velocity, it doesn't matter where they meet, the total velocity is going to be their combined velocity. 3.89 times 10 to the negative third radians per second plus 9.24 times 10 to the negative third radians per second. That's their combined angular velocity just trying to get around this circle. So time equals distance, 2 pi radians, divided by angular velocity, their combined angular velocity, and we wind up with 480 seconds. All right. Whoo, boy, this looks difficult, doesn't it? So the bowling ball is going to roll up the incline, and now we're interested in both the linear kinetic energy of the bowling ball, but also the rotational kinetic energy of the bowling ball. So at the bottom, it has both linear and rotational kinetic energy, and then at the top, it will have both linear and rotational kinetic energy. Now, the great thing for us, we have this equation that has both linear velocity and angular velocity in it. We can change the angular velocity term to be with linear velocity, to be with v. They are related to each other. So if omega is v over r, then I get omega is v over r squared, that whole thing. So v squared divided by r squared. The other substitution that I did there to go from linear kinetic energy plus rotational kinetic energy was plug in a value for the moment of inertia. They told us that the moment of inertia for a solid sphere is 2/5 mr squared, so I plugged that in. So I have 1/2 mv squared, that's something I knew already, plus 1/2 times 2/5 mr squared, that's 1/2 times I, times omega squared. Omega is v over r squared. So I wind up with 1/2 mv squared plus 1/2 times 2/5 mr squared times v squared over r squared. Now, I'm very fortunate that in the second term, the radius cancels. The radius squared cancels. So I wind up with something that's 1/2 times 2/5 mr squared, no, m, fifth m, v squared, because the r squared's canceled. So we'll jump down to here, where we cancel out the mass as well, canceled out the radius in the denominator, and we get 1/2 v squared plus 1/2 times 2/5 v squared equals gh times 1/2 v squared plus 1/2 times 2/5 v squared. So we have the version of what the combined linear and rotational kinetic energy was at the bottom. Then some of that turns into gravitational potential energy, while the rest remains linear and rotational kinetic energy. We plug in numbers. We have everything except for v. So 0.7 v squared plus gh times 0.7 v squared, 25.2 equals 5.39 times 0.7 v final squared, and just keep doing the algebra to eventually come up with square root of the v final squared is v final equals a square root of 28.3, 5.31 meters per second. Hard to just look at this and get the idea, so we'll try to make sense of it later. We were given an initial velocity and a height, and we know what g is. All right, so at a football game, we're going to have conservation of momentum. So assuming momentum is concerned, find the mass of the receiver. So initial momentum of the system is all carried by the one guy who's moving. The final momentum of the system is when the two guys are stuck together. So the initial momentum is 130 kilograms times 4.5 meters per second plus 0, m2 times 0. At the end, it's 130 plus m2, the mass of the second receiver, times their final velocity of 3.6. So I just have one equation with one unknown. I just don't know what m2 is. 130 times 4.5 is 585. 130 times 3.6 is 468. 3.6 times m2 is 3.6 m2. Subtract 468 from both sides of the equation. I get 117 equals 3.6 m2. So m2 equals 117 divided by 3.6. That's going to be 32.5 kilograms, which means that I picked bad numbers when I wrote this question, because you probably wouldn't have a tiny little child playing football with a big person. That was a mistake. Hey, there's two skaters at rest in the center of an ice rink. They push off of each other. The initial momentum is 0, right? Because momentum is the product of mass times velocity. and neither of them are moving. They're standing at rest. The final momentum is also 0. Momentum is a vector quantity. That means one of the skaters has positive momentum, directed in the positive x-axis, and one of the skaters has negative momentum, directed in the negative x-axis. Doesn't particularly matter which one is traveling in which direction. I guess we could assume, I don't know, we don't need to assume anything, we can just pick one, right? So if I say M1 final times V and V1 final, mass of the first skater times their final velocity, mass of the second skater times their final velocity, and all that equals 0, then I subtract one of them from both sides of the equation, and there's my negative sign. So I'm going to say that one of these two speeds is negative. I just have to pick one. I guess I picked the 0.32 because it came first, and so first must be going in the negative x-axis. So negative times 45 equals m2 times 0.42. So I wind up with 144 divided by 0.42. I have a 34.2 kilogram other skater. This can legitimately be two children skating. That one's not a big deal. Hey, this is a similar process to the problem up here with the bowling ball, where we're going to be using that trick where omega equals V over R. Only this time, we have the two spheres starting at the top. They're both going to travel down the same distance, but one of them requires more rotational kinetic energy in order to roll. So it's going to use up more of its gravitational potential energy just by rolling, and it's not going to have that energy to turn it into linear kinetic energy. So the solid sphere, 1/2 mv squared, the kinetic energy, plus 1/2 times I omega, I omega squared. So I for the solid cylinder is 1/2 mr squared. Omega again is V over R. Square that, it's V squared over R squared. So we wind up with a final velocity of the solid sphere of being 4.43 meters per second. But with the hollow sphere, instead of being 1/2 mr squared, it's just mr squared. So when we do the same calculation, GH equals, now it's just going to be V squared. So V equals 3.83 meters per second. So the hollow sphere is moving more slowly when it gets to the bottom, which we would see in a race. All right, so this is dealing with net torque. There's torque that is going down. The downward torque is due to the ball and the arm itself. The ball, force times lever arm, is the weight of the ball times the distance that the ball is located from the axis of rotation. The arm is the weight of the arm times the center of gravity for the arm. The mass of the arm is distributed across the whole length of the arm, so what we're going to do is pretend that all of that mass is located at the center of gravity, which is the center of the arm. That's what they meant by uniform rod. We'll just pretend that all of the mass is located at the center. So that's 0.22 meters of this 0.44 meter long arm. And so we figure out the net downward torque is 3.56 Newton meters. That's torque that is going clockwise. The upward torque all comes from the muscle. The muscle is giving us a force of 12.6 newtons. It's located 2.75 times 10 to the negative second meters from the axis of rotation, the elbow there. So that's our upward torque. So when we figure out the net torque, it's going to be positive upward torque minus the downward torque, and we wind up with a net downward torque. This person is not exerting enough force with their muscle to hold their arm and the ball horizontally, and they will rotate down. Hey, we have a sled sliding along a horizontal surface. Friction is present. We're given some information about the friction. We're given two different velocities. It's going to slow down. So, what is the frictional force? Well, it's horizontal. It's a 100 kilogram sled. So I can figure out the normal force is going to be equal and opposite to the weight of the sled, 100 kilograms times 9.8 meters per second squared. And then I can figure out the friction because it's just coefficient of friction times the normal force. Friction will oppose motion, so I'll just call it a negative value. I can also separately figure out the change in momentum. I have the mass of the sled and I have the change in velocity of the sled. So I can figure out that its change in momentum is negative 1,500 kilograms times meters per second. Therefore, I have a way to figure out the time. The impulse momentum theorem states that force times time equals a change in momentum. So the change in time equals change in momentum divided by the force, and I get 10.2 seconds that it took to slow down. Here's a question that tends to appear on exams, both practice and real life. So we're conserving momentum over 2 dimensions. One car carries all of the x-axis momentum, and I can figure out how much that is by taking its mass, 1250 kilograms, times its velocity, 30 meters per second. That's all x-axis momentum, 37,500 kilograms times meters per second. The other car, excuse me, carries all of the momentum in the y-axis initially. So again, 1,500 times 20, 30,000. Now I have 2 sides of a final momentum triangle. So the adjacent side of my triangle is the x-axis, 37,500. The opposite side, 30,000. So a squared plus b squared equals c squared. Therefore, c, the hypotenuse of this final momentum, is going to be the square root of a squared plus b squared, 48,000 kilograms times meters per second. If I want to convert that into speed, final speed equals final momentum, that's that thing, divided by final mass. What is the final mass? Well, the 2 cars collide and stick together, so the final mass is going to be the combined mass of the 2 cars. And so that's 27,050 kilograms, so 48,000 divided by 2750 gives a final velocity of 17 meters per second. And then the angle, since I know the opposite and adjacent values, the angle theta equals inverse tangent of opposite over adjacent. That's 39 degrees north of east. Whew. I hope the real exam isn't this long. It won't be. But that's it. As always, feel free to ask questions, but hopefully that helps you understand this material.